So this is just kind of a pretty informal StarFOX Plus and Falcon research update, um, since I haven't done one of these in quite a while. So I guess to kind of place this in a broader context here, obviously the lab is doing a lot of work in the various areas of vision-based navigation, whether that's looking more at sort of the swarming side, the space situational awareness side, and also the kind of close range pose estimation side of things. Um, StarFOX specifically is really focused on autonomous swarm navigation using far range cameras. So when the target spacecraft are far enough away that they become essentially point sources in the field of view. Um, and I want to give a super quick rundown of StarFOX just to kind of orient this StarFOX Plus work. So the goal of StarFOX was to advance the state of the art in autonomous angles-only absolute and relative navigation for spacecraft swarms. And there were kind of four like main goals with respect to the previous state of the art. So one was that previous flight tests, some of which Professor D'Amico had worked on, were only for a single observer, single target. So we wanted to generalize that to a multi-observer, multi-target swarm. Another aspect was achieving long-term convergence without maneuvers. So one of the issues is that angles-only measurements are less observable, and often people would use maneuvers to try and improve observability, which is not super autonomous or sort of sustainable. Another aspect is that we wanted to be able to initialize relative orbit estimates without requiring like an a priori orbit info from the ground to improve the onboard autonomy. And finally, one of the concepts was that in the past, the observer spacecraft had relied on having GPS on board to maintain its own absolute orbit while it was doing relative angles only nav. But it turns out that when you have a swarm with multiple observers that can kind of share measurements, they get improved observability and can maintain their absolute orbits as well, long term without necessarily requiring GPS updates. So StarFOX relied on something called the Artemis architecture, the absolute and relative trajectory measurement system, where we have instances deployed on one or more cooperative observers to track one or more non-cooperative targets. Some key aspects are that it is angles only, so we get bearing angles from onboard vision-based sensors or cameras. It's distributed, so different observers might be estimating a subset of the complete swarm state. It's also cooperative, so we have a cross-link or an intersatellite link here where we can optionally share measurements between observers. It aims to be pretty much autonomous, so sort of minimal reliance on external interaction, and is also miniaturized, so it wanted to be suitable for small spacecraft, all that sort of low SWaP-C hardware. And this was the block diagram of the Artemis architecture. At sort of a super high level, the dark gray areas here are the sources of measurement information. So, for example, we have the vision-based sensor on the top left here. We have the exchange data in blue and the three core software modules in green. We have image processing, which runs about once per minute, and that takes images from the camera and essentially turns them into bearing angles for potential targets in the field of view. We have the BOD or batch orbit determination module, which runs around once in orbit, which uses the batches of bearing angles from image processing to create initial relative orbit estimates. And then we have SOD or sequential orbit determination, which runs around once per minute again, which uses new measurements from the camera on board, as well as potentially measurements from other observers over the crosslink to refine the system state estimate. So StarFOX was very successful. I won't sort of go through this slide really, but we defined a bunch of key performance parameters pre-flight and were able to achieve pretty much all of those either through on-orbit experiments or through post-processing the flight data on the ground. So this was all great. Now, one thing I wanted to talk about actually is the status of the swarm currently, because this has kind of become a bit of an issue where there are four spacecraft in the Starling swarm. There is one guy, SV2, who is having a great time. There is another guy, SV4, who's having also a great time. There's also SV1. SV1 is like a little bit on fire. So it has like a faulty radio, which means we can't really interact with it in like a lot of meaningful ways. But NASA are working on a way where we can like use the crosslink radios to like transmit stuff from the ground to like SV2 and then SV2 crosslinks it over to SV1, which might work. We'll see. And we also have SV3. SV3 is sort of dead right now. It's like floating away slowly, and no one knows really how to talk to it anymore. It's like in a safe mode, I think. So, uh, as you can imagine, this is kind of an issue. We've only really got two working spacecraft out of four, which is not ideal, but it's enough to work with for StarFOX Plus. So the goal for StarFOX Plus really was to kind of expand the reach of the algorithms here, focusing on a lot of space situational awareness kind of work. So to essentially, take StarFox's successes and build upon them to demonstrate improved performance and more general applications. So there are five distinct applications here. I wanted to just kind of talk about two of them today. Um, First of all, we have identification of cataloged resident space objects, or RSOs, which is useful for kind of space situational awareness. If you have like another object not in your swarm passing through the field of view, you kind of want to know what it is and maybe use that information. Um, we have fast initial orbit determination. So the current batch orbit module takes around 90 minutes to generate a state estimate. It's obviously useful to be able to do that more quickly. We have estimation of auxiliary states, such as drag coefficients, clock offsets between observers, stuff like that. So not just the orbit state. Uh, Data fusion with intersatellite ranging. So we have the crosslink already to trade bearing angles. Why not use it also for ranging measurements as well? Because that's one of the weaknesses of angles only is you don't get good range information. So we have the ranging there. We should try and apply that. And finally, adaptive state noise compensation. So this is an algorithm that Nathan Stacy developed to do like adaptive process noise estimation. So if you don't have good dynamical knowledge of your environment, being able to have the filter react to that more robustly. Um, okay, so the StarFox Plus architecture is very, very similar to StarFox in that it's just built on top of it, essentially. The main differences are kind of the two orange blocks here, which are data files on board. In this case, a catalog of stars for star identification and a catalog of resident space objects for RSO identification. And that's one of the things I wanted to talk about is the image processing module, which has now a new algorithm for identifying resident space objects that pass through the field of view. Okay, so this is an overview of how this algorithm works. I have stolen this slide from Mike, actually, who did a lot of this implementation, so credit to him. But broadly, the flow of it kind of works like this. So we get a new image from the onboard camera, and when we do that, we have a catalog of all the space objects in the sort of space track catalog that's maintained by the US government. It's a set of two-line elements for each object. And so we uplink basically a text file of that catalog to the spacecraft, but before each experiment, roughly weekly. And when we get a new image, we propagate the orbits of all these objects to the time of the current image. Now, it's a lot of objects, up to I think around 22,000 in the full catalog. So we can't use a super fancy propagator, but there's an analytic model called SGP4. I think it's like Simplified General Perturbations 4, which was developed by David Vallado, I think. And he had something to do with it, at least. And it enables you to do very fast analytic propagation, which includes things like some J2 and some drag effects on board. So we do this, we check which of the objects are expected then to be in the field of view of the camera based on things like how far away they are, sort of the angle between them and the camera. Something we also have to do is estimate the uncertainty in those two-line elements. So the catalog actually doesn't come with uncertainty currently as like a standard format, which is kind of a problem for a lot of space situational awareness purposes. So we had to come up with our own uncertainty model. So the way we did this is we came up with an empirical model where we compared the two-line elements from the catalog for the Starlink spacecraft with the sort of ground truth orbits from GPS. So we had access to that data for Starlink, so we could plot the errors between the GPS ground truth and the catalog over time. This is actually what this figure shows for the different relative orbit elements. These are kind of like the ROE errors between the propagated orbit and the true orbit, where there are different colored lines here. The black one is like a kind of numerical propagator with full fidelity dynamics. This blue one is the numerical integration we use on board Starling inside the navigation filter. And this red one is the SGP4 analytic model. So clearly SGP4 is not super accurate. You're getting like, say, on the order of a kilometer or two of error per day. But, you can still use it to do very fast propagation. And so we developed a numerical uncertainty model based roughly on these numbers and transform that into bearing angle space. And then essentially, compare the distances between any unknown objects we see in the field of view to where they're predicted to be from the catalog and their uncertainty regions, and do an optimal match based on geometric distance, Mahalanobis distance, and things like this. So the current status of this is we have tested this using some flight images. So these are images from March last year where we ran the flight code on these images, and the green crosses and circles are the catalog locations of the starling swarm. So they're kind of in the center of the field of view here. Whenever this video pauses and you see like a white ellipse and a white cross, that was a catalog object outside the starling swarm. So that's, when we've spotted something in the field of view and we say, okay, this matches roughly where we expect catalog object 53051 to be, or something like this. So we've done all the pre-flight validation and have uploaded the sort of new versions of the StarFOX apps onto the spacecraft. And we've done some initial tests where we try and treat the Starling swarm as kind of the unknown catalog objects, and also some initial tests where we do it for Starlink constellation satellites as well. There are some issues here in that the catalog is quite big. So if you're using sort of our current format, the full catalog of 20,000 objects is around 4 megabytes, and roughly anything higher than 1 megabyte is kind of tricky to uplink to the swarm, or requires like a special procedure. So we have to come up with ways to like filter the catalog to what's necessary, or compress it, or come up with more efficient data representations. We also had a number of crashes on board to do with essentially a bunch of source code files weren't linked together properly. So whenever image processing tried to like call the SGP4 propagator, it crashed. It's sort of weird because it didn't crash and we were testing on, say, our machines in the lab, and didn't throw up any compiler warnings either. But I guess something there didn't get linked together, so it ended up crashing for a while before we figured out that was going on. But here are some initial tests, actually, of Starlink identifications. I appreciate that this is very small. So here is a zoomed in view where you can see this green location. This is where we expect the Starlink satellite to be from the ephemeris that SpaceX provides. So they sort of, as a public service, provide their own orbit estimates, which are pretty accurate to within tens or maybe a few hundred meters. So better than the two-line elements or TLEs. So the white region is where StarFOX expected it to be on board. And as you can see, we get a pretty good match between this little object here and the SpaceX thing and what it was identified as by StarFOX. We have another example here. Again, very hard to see. So another nice aspect of this particular one is that you can see that because this object has a high relative velocity kind of across the camera frame, it's a little elongated because the camera has like a 50 millisecond exposure time, so it travels a little while across the frame during the image taking. And you can kind of see that, which means, it's probably likely some kind of resonant space object, and it makes sense for it to be like a Starlink satellite. Here's another couple of examples, specifically where we saw this particular Starlink object twice in two separate orbits. And again, since the match is pretty good with this green SpaceX solution, we can be reasonably confident we identified this in flight. So this is all pretty promising. And yeah, we're doing some good initial results for the RSO identification part. The other aspect I wanted to talk about today is the fast batch orbit determination system. So uh, for a bit of context here, I wanted to introduce first the existing BOD system. Um, so this is where I guess the presentation starts to do some snorkeling, as Simone says, where there's actual maths. So we consider a batch of bearing angles of y across some set of epochs t, which is dependent on the system state x at some time. Um, and we know that target range is weakly observable with bearing angles. So the same kind of ellipse of bearing angles could be something close to the camera moving very little or something far away that has a large relative motion. Um, so what we do here is to combat this, we define an initial relative orbit element estimate x and a set of samples of delta lambda, where delta lambda is the ROE, which kind of most corresponds to that weakly observable range for StarFOX. And for each sample, we compute this delta z quantity, which is the difference between the measured bearing angles from the camera and the bearing angles that we model based on a current state estimate. And we update the estimated state to reduce this delta z residual by something like iterative batch least squares. And we produce a plot like this on the bottom here, where on the x-axis we have the delta lambda samples. On the y-axis we have this converged delta z residual. And we sort of pick as our output this delta lambda sample that produced the least residual. So we do something that SLAB loves to do here by kind of exploiting the relative orbit elements to divide our state into weakly and strongly observable components and using different estimation techniques for each one. Another thing we can do is we can actually use these converged residuals to give us to kind of give ourselves an estimate of the initial state uncertainty without necessarily knowing much about the performance of the sensor and the dynamics model and so on. However, we have a problem because the current BOD system takes 90 minutes to generate an orbit estimate, or like roughly, one or two orbits of measurements, which is not ideal if you want to be like responsive for like a space situational awareness kind of application. So what if we could take 5 minutes to generate an orbit estimate? Wouldn't Simone be happy with this? And this was kind of what we wanted to try and do with StarFOX Plus. So in terms of the multi-observer system, really the goal is to like, you have some line of sight vectors to your target. You want to solve for this six-dimensional relative state vector, which could be Cartesian or ROE based. So you have your line of sight unit vectors, and what you have to work with is you have a set of constraints where your line of sight vectors are parallel to the relative position of your target, where, this relative position is what you want to be solving for, essentially. You also know that your system is subject to dynamics. So for example, this is kind of the traditional linear dynamics model, which maps the relative orbit elements to the RTM position of your target. And so what you can do is you could, for example, substitute this dynamics model into your constraint equations and generate some kind of system of equations where this B vector is sort of the coefficient of your dynamics model here. So you have this system of equations which you can theoretically solve. The issue is that each line of sight measurement gives you two linearly independent constraints. So in theory, if you have three sets of bearing angles, you have six kind of equations to solve for your six relative orbit elements. The problem is that this is a homogeneous linear system where you can actually scale the solution C by any amount and still get a valid solution. So this is kind of the traditional angles only scale ambiguity. One possible approach to this was done in a lot of Matthew Willis's work was he derived second order polynomial dynamics models. Instead, if you substitute this into the linear system, you get a polynomial system, and that gives you a definite solution for your target range as well. And yeah, so you can solve for your six state components using only three bearing angles. So there were a couple of issues with this in that because you're using only three bearing angles, it's very, very sensitive to noise. Also, it gives you an estimate for your relative orbit elements, but no idea of your initial state uncertainty. And to initialize a filter, you need some kind of uncertainty estimate too. So another possible approach we looked at for this is instead using two observers with known absolute orbits to kind of eliminate the scale ambiguity because they have this known baseline between them. And you can pretty much then triangulate your target's position with respect to your observers. So instead of three measurements from one observer, we have three measurements from two observers, and kind of taking advantage of the fact that we have a swarm to work with. The problem here is the output is still quite sensitive to measurement noise. Because the StarFOX star trackers are sort of not great, you have like, 20 to 40 arc seconds of noise. And for this to like perform well, you want kind of like on the order of, say, 2 or 5 seconds arc second, 2 or 5 arc seconds of noise, much less. And again, your output, you're still solving a linear system essentially, so you get a solution, but no indication of its quality. Um, so what we choose to do here for this StarFOX Plus thing is we kind of do a sampling based approach where we say that like over a 5 minute period, we got like, a bearing angle every minute. And we kind of randomly pick sets of three bearing angles from within that time period. And we say that's like one sample. And we use those six random bearing angles to compute a state estimate. We then choose six other random bearing angles to compute a state estimate and generate a bunch of state samples in this way. And then through those samples, we get a mean and covariance, and we kind of try and average out the effects of some of the individual bearing angle noise. Um, so for this, we have done a lot of the pre-flight validation. Kind of the goal here was, using batches of 5 or 6 measurements from each observer over a 5 minute period to try and generate an initialization. This plot on the right here shows cumulative distribution functions of the relative orbit element errors in blue and 1 sigma on 3 sigma uncertainties in red and green for state initializations in kind of a Starling-like scenario using this method. So you can kind of see that we get, relative orbit errors on probably the order of several hundred meters in most cases, going up to a few kilometers for the delta lambda range error. But the errors are pretty well characterized by the uncertainty we're generating. So overall, hopefully, we are able to use this method in flight to initialize the orbit estimate. However, there is an issue because, as I mentioned, we have this issue with SV1, where SV1 is our current target for our swarm, but that's got a very unusual and large relative orbit because of its various issues, which means both of the observers can't really see it most of the time. And the problem is we implemented a multi-observer BOD method where multiple observers can't see the target. So one other option is maybe trying this for a Starlink satellite instead, because Starlink satellites are bigger, so they are sort of more generally visible from a longer range. On the other hand, Starlink satellites have a very fast relative velocity, so they're not in the field of view for very long, and that creates other issues where you kind of have to actively point your camera at them. So the trade, I guess, between trying this for SV1 and trying this for a Starlink satellite is currently being looked at. Okay, the final couple of slides here are instead looking at the most recent work here, which is called FALCON, which adds a resilient positioning component to this side of things. So FALCON is called, essentially stands for Fast Autonomous Lost in Space Catalog-Based Optical Navigation. And it builds really upon the concept of StarFOX and StarFOX Plus, where again, we're using onboard cameras to get bearing angles to resident space objects. Like with StarFOX Plus, we're matching those RSOs to identities in a space object catalog. And then we're saying those RSOs kind of can act as position beacons or, beacons with known positions with respect to the observer, to the camera, with some uncertainty. And we can use that to essentially triangulate our own position in space. Now, StarFOX Plus assumes the observer has kind of an initial orbit estimate to work with. But for FALCON, we relax that assumption and we say, even if we have no knowledge of the observer's position, we can still do this catalog matching and triangulate our own orbit. And then sort of moving on from that, we can potentially fuse measurements from multiple observers and feedback measurements into the catalog to improve our space situational awareness accuracy. So the current status of FALCON is, we have a block diagram, which is very similar again to StarFOX Plus. where kind of the key addition is this lost in space catalog matching block, which is something that actually Antonio has been doing a lot of work on. Um, Something Toby has also had some great ideas for how to actually make that work, where given a set of unit vectors in the field of view to random objects, given a set of catalog data, how do we find the match between our own position and which of these objects correspond to different catalog objects? So the current status of this is that Antonio is busily coding Falcon in C++, um, having a great time doing that. Uh, we have initial prototypes developed for kind of the lost in space catalog matching, as well as for the optical orbit determination using RSOs, with steps 4 and 5 to follow in the future at some point. The goal actually is to, once StarFOX Plus is finished in later this year, we would like to then use the Starlink Swarm to fly Falcon as well in 2026 for on-orbit demos. This is kind of one of the initial demonstration simulations where we are using resident space objects as beacons to do autonomous optical positioning in kind of a GPS-like fashion, but just using optical measurements, where this is the absolute orbit estimate of an observer in the quasi non-singular orbit elements, where this gray region is the amount of state uncertainty, and this black line is the amount of state error. So you can see we kind of start off with a pretty coarse 5 or 10 kilometer uncertainty in each of the orbit elements, which is sort of what we expect as maybe the output of the lost in space catalog matching algorithm. And then over time, we are able to use new RSOs. So every time you see a red dot, it's because an RSO was identified. And you can kind of see it behaves in a way like, say, how the number of GPS satellites in view changes over time. We get a different number of RSOs in view with each image. And we're able to use that to narrow down the position uncertainty pretty well to around 100 meters in most of the orbit elements, to a little larger in the mean argument of latitude, which is kind of, I guess, the along track direction. This is because the camera is pointed in the along track direction, so you get like a dilution of precision, where all of your measurement information is kind of aligned in the along track. So when you triangulate stuff, there's a kind of a lot of uncertainty in that direction. So there are potentially ways to fix this by like having a more varying observer attitude. It's something we're looking into here. I think that's pretty much it. So I have one final meme here you can read. But StarFOX Plus extends StarFOX algorithms for improved performance and SSA outcomes with the first identifications of RSOs in flight. Next step is Falcon, where we want to try and extend this to lost in space autonomous optical positioning, potentially in 2026. There's also something called Lunar StarFOX, where we want to aim to apply StarFOX to support NASA's kind of next generation lunar swarm ideas. This is some work that's been done in simulation already, so we can, support this pretty well. But the actual kind of timeline of that is a little unspecific in terms of when this would actually happen. But yeah, I think that's all I have. Thanks for your attention. Happy to take any questions.